So we just started talking about continuity and what it means to be continuous at a certain value, how to show that it's continuous there or not continuous there. We talked about there was 3 properties that had to hold if it was continuous at a value. So first of all, it had to exist at a value x equals c. The limit had to exist as x approached c. And then also the limit as x approaches c also had to equal f of c. So looking at the following examples, first we're going to look at some graphs of this, and at the end of and look and show that it is continuous or not continuous. Then we're going to look at some equations. Yesterday at the end of the lecture, we just kind of talked about what could be happening graphically if it was discontinuous at a value. We talked about there's one type that basically that could be removable if you fill in that hole there and define it. We had a jump discontinuity, one that is caused by vertical asymptotes, and then we had values that were oscillating really quick between 2 values. So find all the values x equals a where the function is discontinuous. For each point of discontinuity, we want to first figure out what f of a is. If it exists, we want to look at the left-hand side. We want to look at the right-hand side of that limit. If those are the same, then we know that limit exists. If not, that limit doesn't exist. And then we want to identify if f of c equals that limit. And if so, then all those conditions are met, then it is continuous. Okay, so for first part again, find x equals a, and hopefully you've already notified where this was discontinuous. And so right here at -1. And so first of all, it asks us f of -1 in our case, if this exists. So does f of -1 exist? What do you guys think? So looking at participation or participants, go to participants and then either click on the green yes or the red no. That way I see you all there together.
Where do we click?
Excuse me?
Where do we click?
Okay, so if you move your mouse, you'll see the participants down on that horizontal row. If you click on participants, on that bottom of participants, you'll see yes and no. Go slower, go faster, and just either click yes or no.
Okay, thank you.
Yep. Okay, so 12 out of 17 have voted, no, 13. You got pretty much half and half, 7 yes, 7 no. If I zoom in a little bit, and you can always change your vote. Okay, so a couple of you maybe changed it. Yeah. So 8 yes, 6 no. Okay, we got the yes, the yes has it. Can I speak? So notice that at x equals -1, if you go up here on the graph, here is a solid circle, and so this is actually a point on the graph. So this f of -1 is saying what is y when x is -1. So f of -1 does exist. If those were both open circles there, then it would not have existed. So does f of -1 exist? And this is yes. And we can even state further that f of -1 is equal to the y value, so is 2. Another way to say that is -1, 2 is a point on the graph on f of x.
I have a question about this.
Yes.
If the open circle was where the position of the closed circle is right now, would that mean it would still exist or not?
It wouldn't. So if those were both open there, then it would mean that it does not exist.
Right,
So,
but what if they switched places is what I was asking. Like
yeah,
if
so they
the
switch places.
open circle first.
Yeah, so if this was open first and then this one was closed, it would exist. So it's just that because this is closed, this is saying that that's the point instead of this. This one's getting really, really close to x equals 2, but never gets there. Where this is closed, so it actually exists.
Okay, so in that case, it would be -1, 4.
Exactly.
Got it.
So here when it says look at the limit as x is approaching, in our case we're looking at -1. So the limit as x is approaching -1, and it's telling us to look at it coming on the left hand side. So values that are smaller than this -1. And so go up to the graph. And so x values that are smaller than -1 uses the graph on the left hand side. And as we come up, it actually includes it, but it would have still been a limit on the left. And so that value right there gives us back 2. And then it asks us to look, okay, now let's look at the limit as x is approaching -1 on the right-hand side. In that case, we're looking at x values which are bigger than -1, which is this graph. And so we're looking at what's happening as x gets closer and closer to -1, our y value. So that's actually not equal. The limit as x approaches -1 on the right-hand side of f of x gives us a backup value of 4. And so we talked about in order for a limit to exist, the left and the right had to be the same. We can talk about left-hand limits and right-hand limits like we were talking about before, but in this case, the limit itself doesn't exist. Okay, so from there, you want to identify which condition or conditions for continuity are not met at x equals -1. So first of all, it had to exist. When x was -1, it had to be a point on the graph, which it did. The next condition was, or one of them was, that the limit had to exist. And we just showed because the left doesn't equal the right, it doesn't exist. And so here's one condition that this is a condition not being met. To be continuous at x equals 1. Anywhere else on that graph, there's no jump, there's no other open holes, and so it's continuous everywhere else. That's the only problem we have with that one. Any other questions on that?
Yeah, I have one.
Okay.
So since there's only those points right there on that specific asymptote per se, both ends are continuous, which means it is continuous. It's not going to, stop anywhere else.
It's not going to stop anywhere else, right? And there's not going to be any other open circle. This actually isn't an asymptote. And we do have, like we talked about before, left limits could exist and right hand limits could also exist, but it doesn't mean that the limit itself exists. And so because they were different, it doesn't exist.
All right.
And because it doesn't exist, that is one of the conditions that had to be held to be continuous. Those three that we have to show, which will be back up here somewhere. Maybe not. So in order to be continuous, those three have to hold. And our second condition in our case didn't hold. Technically, the third condition in our case also won't hold, because if our limit doesn't exist and we knew that f of c in our case was equal to 2, well, it doesn't exist and 2 are not the same thing. So that's another condition we could say that didn't hold in that case. So here's another graph. And so looking at this graph, where is that discontinuous, if anywhere? You cut out a little bit, but I think you probably said the right thing.
-2?
So at x equals -2?
Oh, wait, no. X equals -1.
Right, so x equals -1? That would be right here.
Oh my gosh, I'm getting mixed up. 1. X equals 1.
Okay, yep. I see what you were doing. You were telling me the y values.
Yeah.
So you're right. So it's x equals -1. So that's where we're looking, the x value, where there's a jump or an open circle or a vertical asymptote, or maybe oscillating. But so x equals 1. Continuous. And then, then one of the questions was, does f of 1 exist? Okay, so what do you think in that case? Yes or no on that participants? I was wondering if someone was going to be afraid to say no after everybody said yes. Or not everybody, but a lot of people said yes. Okay, so it's going to be defined at x equals 1 if, so think of it as a vertical line through that x equals 1. Is there a value where we have a point on the graph there? And if we do that, it's open here, so it's not, but up here we had a point. And so since we have a point here, it is defined, and it's defined when x is 1, y is going to be 2. So f of 1 is 2. A function, it could really only have one point passing the vertical line test. Okay. So now looking at this, let me clear your results. Do you think, not looking at left or right, do you think, well, you can look at it, but I'm not going to ask you on that. Do you think that the limit exists at x equals 1? Does that limit exist at x equals 1? Okay, so a limit exists if the left and the right-hand side are coming to the same y value, getting closer and closer to the same y value. It actually doesn't have to exist at that value, y value, but if it gets closer and closer to that same y value as we're coming in on the left, so notice that y value on the left-hand side, that's -2. And the y value we're getting closer and closer to as we come in on the right-hand side is also -2. And so the limit actually exists. So limit as x is approaching 1 of f of x, I can say is equal to -2. So the last one says, we show that f of 1, does this equal? Does f of 1 equal the limit as x approaches 1 of f of x? Are they the exact same value? No, we saw, right? One was 2, and we saw that one was -2. And because that condition doesn't hold, this tells me that this is not continuous. So not continuous at x equals 2. Okay, so one more graph. Where, if any, would you say that this is discontinuous?
At 0.
Okay, so x equals 0. So first question then is, let me clear that. Does f of 0 exist? So 2 of you say yes, 8 of you say no. There's actually this vertical asymptote here. So the graph, as x is getting closer and closer to 0 on that left-hand side, it's going to be getting closer and closer to, or it's not going to be getting closer and closer to, it's going to be continuing to shoot downwards. And it's never actually going to reach here. It's going to look like it hits there, but it's never actually going to reach there. Same thing as we're coming closer and closer to 0 on the right-hand side. This also goes down forever. Getting closer and closer, like hugging that line, but we actually never get there. Because it's, and so there's no point here on this y-axis. There's no, the graph never touches this or has a point on this in this case. And so in this case, f of 0 does not exist. Okay, so there's a vertical asymptote. At x equals 0. So graphs can cross different types of asymptotes, but they can never cross a vertical asymptote. Graphs never touch or cross a vertical Just gets really, really close to it. Okay, what about the limit? Does a limit exist there? Does a limit as x approach 0 of f of x exist? So it will exist if it goes on both sides to one value, and that one value that they're both heading towards is the same. If I look at the limit as x is approaching 0 on the left-hand side, there's no one y value it's going to hit. It's just going down forever. And so the limit as x is approaching 0 on the left of f of x, this is equal to negative infinity. That just tells us the direction it is, but it doesn't exist. Same idea, the limit as x is approaching 0 on the right-hand side of the graph of f of x. There's no one y value it's going to go to. It's always shooting down forever. And so this doesn't exist. I can put that at negative infinity. Again, that's just telling me more about what's going on in the graph there. But something that approaches infinity or negative infinity, not one y value in general, then doesn't exist. So this is actually no. So right there, that one condition isn't met, and so it's not continuous. Okay, what about, hopefully that clarified things. Is there any other place in there that is not continuous? Okay. So I see yes. Where is it? I see you know.
X equals 2.
So look at x equals 2 here. If we go to x equals 2 and we go down to where the graph is at x equals 2, notice this is, maybe you can't see it maybe, but that's an open circle there. I just closed it. So that's supposed to be open. And since that's open, that means it doesn't exist unless there's some point above x equals 2, which I don't see, or below x equals 2, which I don't see. And so x equals 2 is also a place where it's not continuous. And the first condition is that it has, there's no open circle. So f of 2 does not exist. And then the limit though, so it's possible not to be continuous or it to exist at a value, but this does have a limit. And if we look at that, the limit as x is approaching 2, on the left and the right are heading towards the same y value. So left, right, that y value that it's getting closer and closer to is -2. So this is -2. But this is the condition that needed to be said in order for it to exist. So because of this, we can stop and say x is not continuous at x equals 2. Okay, so when we were looking at limit rules, we said that, you know, if a limit as x approached a value c of some function exists, and the limit as x approaches c of another function exists, then we could break down our limits. We can use rules like this too with continuity. And so the following property holds. So if you have a function f and g that are both continuous at x equals c, then we can use the following algebraic combinations and say that they're also continuous at x equals c. So the sum of those two functions will still be continuous. The difference of those two functions will still be continuous. A multiple of a constant times a function times another function, a function divided by another function, as long as g of c is not 0. Can't have 0 in the denominator. Unless it's also in the numerator, then we gotta look at it because it's an indeterminate form and it doesn't tell us anything. If you have some function that's continuous and you raise it to a power, an exponent of n that is positive, then we can say that's also continuous. You start getting in problems if you say that n is negative, then that takes your function f of x down to the denominator, and that's why they have to put that stipulation there. And we have to worry about variables down in the denominator not being continuous at values that set that to 0. The other rule that we also have to have a little stipulation on there is that if f is continuous and we took the root of that function, then that would also be continuous. But on here, we have to make sure that n is an even, or it says a positive integer. I'm thinking we also need to be careful though with values where it's undefined. So values where f is less than 0 if n is positive, as even. And this is just saying n is even, meaning again, negative exponents would bring that down to the denominator. Another one that's really interesting and is going to be really helpful for us is this one on composition of continuous functions. So again, we have two functions that are continuous, f and g. And if we can say that f is continuous at c, and if you look at, and g is continuous at f of c, then we can say the composition of g of f is also continuous at c. So just kind of recall composition of functions. You denoted that with a little circle in between the two functions of x. Another way to write this is saying that you're going to look at plugging in your equation f of x wherever you saw an x in g of x. Another way, so up here, this is basically saying g of f of c, where x is equal to some c. Another way to write this is you're going to first plug in c into the equation f of x. Well, we know f is continuous there. F of c is our y value we get back. And so is g of that y value is also continuous. And g is continuous there. Then we can say the composition is continuous. Which I really wanted to, and I don't know if I should start harder. So maybe I won't. Other things that are kind of helpful too is to know about your different types of functions and where they're continuous and where they're not continuous. Knowing how to find that domain of your function is helpful. And so different types of functions we know about. Polynomials. We've worked with a lot before in the past in different math classes, but that's when your exponents are always positive and they're always integers of your variable. And we're going to say that our coefficients in front are real numbers. We're not going to deal with imaginary numbers here. So polynomials are great because they're continuous everywhere. Rational functions, that's where we have, in this case, our numerator and our denominator are both different polynomials. This is going to be continuous anywhere except for when x is equal to 0, or q of x is equal to 0. The value, the polynomial in our denominator can't be 0. So looking at radical functions, root functions, y equals the square root of ax plus b underneath that radical. We have to be careful because if we have and this could be the nth root where n is even, then we have to be careful because then what's underneath the radical, ax plus b, has to be greater than 0. And if it's not, then we get an imaginary number and that's not part of our domain. And so it's not even going to have any piece of the graph there. That's odd. We can have negatives underneath the radical and get back to real numbers. We're okay there. You should be familiar with what your exponential functions look like. Y equals a to the x power. Here's a case where a is greater than 0, so it's increasing strictly. It's going to be in this form always. If your base is bigger than 1, it's actually is always in this shape. This we should also say a is greater than 1 here, because technically if a is less than 1 and bigger than 0, the graph is going to be decreasing and looks like this. But there's no place where this is undefined for x, so it's continuous everywhere. Log functions are inverse functions of our exponential functions. And there is a rule in here, which I didn't state, that says if a function is continuous, then so is its inverse. And its inverse is also continuous. You just got to work. You have to think about domain and range of functions and their inverse. They're swapped. So notice here our range is from 0 to infinity. Those are all the y values that you're hitting. Our domain are all real numbers for our exponential. But here our domain is from 0, not including, to infinity. So that was our range up here. And our range in this case is all real numbers. It's going to hit all the y values, which was our domain over here. Okay, so let's look at the following and find where the function is discontinuous. And I'm just going to grab one of these or grab one of them from your book. I think I'll grab one from your book because they're a little more maybe difficult. Okay, so it says apply the continuity test. At which point do the functions, oops, wrong direction, wrong problems. So At what points are the functions and exercises 13 to 32 continuous? Okay, so example. So let's find where the following functions are continuous. So let's say we had y is equal to the fourth root of 3x minus 1. So first thing you want to do is we want to look at the domain. So let's find the domain. So when looking for the domain, I go towards what are my trouble spots and exclude those. And I'm going to have trouble spots if I have a radical if this index, this number here is even, which it is. And so I know what's underneath my radical has to be either, in this case, it can equal 0 because it's not in the denominator. So it can be greater than or equal to 0.
Real numbers.
Your mic got really bad. Your mic got really bad. That absolutely destroyed my eardrums. I don't know what happened.
Is that better? Just pausing a second.
Much better.
Yeah, that's better. It periodically happens. It's happened since last semester.
Yeah. You know, and my husband was in a meeting earlier. My nephew's now here, and he was tutoring. He tutors. So sometimes we're all on, which is not the best. I don't think for things going smoothly all the time.
Definitely jump scared the hell out of me. Anyways, you're good now.
Well, hopefully I woke you up if you were falling asleep.
Just don't worry. I'm wide awake now. Don't you worry.
So we were looking at where it's continuous. We were looking at finding the domain. Domain is where the values are, we can put those values in for x and get back a real number. So looking for domain, sometimes looking for trouble spots is helpful. And so looking at a radical, if this is even, we're looking at when is this bigger than 0. And so looking at when is 3x minus 1 greater than or equal to 0. Well, it's linear inequality. You solve inequalities differently. But linear, we can just solve it like we were solving for x. Just worry about if you're dividing by a negative. So add 1 to both sides. We would get 3x is greater than or equal to 1. Divide both sides by 3. And so we get x has to be bigger than or equal to 1/3. Well, 3x minus 1 is a polynomial. So I know if I chose f of x equals 3x minus 1, I know that this is continuous everywhere. Because it's a polynomial. And I know if it's continuous everywhere, that means it's also then it has to be continuous. On my set domain, right? From x is greater than or equal to 1/3. Then we also had that rule above that said, well, hey, if you look at a function, what's underneath the radical, if that's continuous, then it's also going to have to be continuous if we took the root of that. And this was a positive number, which it is. And so then, oops, come on. So then the fourth root of 3x minus 1 is also continuous. If x is greater than or equal to 1/3. And so another way to write this, and they might ask you on my math lab to put your solution where it's continuous in interval notation. And so since we're including the 1/3, we're going to put that bracket, and then we're going all the way to infinity. I just want to do one more just because it looks really fun. And I'm noticing, you know, there's a lot of problems in here that we could spend a lot more time on. And so I might just take an extra day on this section because this, again, this material right now is pretty important for the rest of the course. But I want you guys to take that time this semester, or not semester, this weekend. Hopefully you can use this time to catch up where you guys are weak. So the limit as x is approaching pi, we want to look at the sine of x minus the sine of x. So this didn't ask me to, okay, so find the limits of the following problems. Are the functions continuous at the point being approached? So trigonometric functions, sine and cosine, if you remember and you look at the graphs of those are continuous everywhere, from negative infinity to infinity. It was the trigonometric functions we had to worry about where if we rewrote them in terms of sine or cosine, we had to worry about what value set the denominator equals 0. But trig functions are continuous everywhere. So let's look at this and keep. For some reason, there we go. We can look at this, and there was a rule that says we can look at this as the sine of the function, the limit as x is approaching pi of this piece here, x minus sine of x. We could even break it down further where we're looking at that limit of the difference, but I'm not going to do that. Just pull that down. Okay, so we have plugging in pi here. We actually probably could have just gone in here and plugged in pi wherever we saw next. Could have saved us a little bit of time, but let's just do it now. So we have sine of pi minus sine of pi. So let's simplify inside that parentheses, and let's remember what sine of pi is. Well, if I think of my unit circle for a second, I know sine is my y value, pi is over here. Y value here on the negative x-axis is 0. So sine of pi is 0. So this gives me pi minus 0. Which is the same thing as sine of pi. And sine of pi, we just discussed, is 0. So okay, so the limit exists, and we wanted to know if it was continuous there. And how I was kind of explaining before that sine is continuous everywhere, And we were just talking about that rule of continuity with a composition of function. And so if I look at the function that I was plugging in wherever I saw an x in sine of x, which would be x minus sine of x, both of the o's are continuous. X is continuous and negative sine of x is continuous. So because of that theorem, I can say that this whole thing is continuous there. So I stated it, I didn't write it because we're out of time, so yes. Continuous there. X equals pi. Okay, so like I said, we didn't finish this. I thought I would, but we will finish that on Tuesday since Monday is a holiday and we won't have class.